Now 5.2 will be all about the graphs of polynomial functions, and we're going to be doing, as you can see, the lesson goals. We have a lot of things to cover. It's just a lot of little things, so it's a lot easier than it seems. This list looks intimidating, but it really is a pretty straightforward idea. So by the end of this lesson, we should be able to identify polynomial functions, directly evaluate them, synthetically evaluate them as well. The second and third bullet point, these two guys are just alternative methods of doing the same thing. We'll be able to find this thing called end behavior polynomials, and finally, lastly, to sketch polynomials, which we already have a method to. It's the same method we've been doing whenever we sketch graphs in general. As always, let's go ahead and start with a couple of vocabularies and ideas, just so we have, we're speaking the same language. What is a polynomial? Simply put, it's a monomial or a sum of monomials. And monomial is, again, a cluster of letters and numbers put together. For example, 3x is a monomial. So if you have a 3x by itself, or a collection of algebraic expressions added and subtracted to each other, we call it a polynomial. Now, if you make him into a function, polynomial function, he has a set of rules. So let's go ahead and write down the formal textbook fancy schmancy definition. A polynomial function in standard form has the following structure. Now, I will admit this is going to look super duper intimidating. Just go ahead and follow along, write it down, and I'll break it down piece by piece, and you'll see that the definition is actually pretty straightforward. So it's f of x equals a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power plus a sub n minus 2 x to the n minus 2 power plus, I think you guys get the idea. You just keep subtracting over and over and over until you get down to 1, and then you finally get down to 0. So that's the formal fancy schmancy definition, but once you understand what each piece means, it's pretty straightforward, right? A sub n, actually let me say this, a sub I are called coefficients, right? Notice how the a's are always in front of the x's, and numbers in front of letters are what we call coefficients. Specifically, a sub n, the very first one, is called the leading coefficient. The last one, a sub naught, is called the constant. And there's one extra super duper important idea here. Right. This n here has to be a whole number. A polynomial function has a strict rule. The exponents, notice that's what n is, right? Let me highlight. There we go. This n, n minus 1, n minus 2, so on. They have to be positive whole numbers. If it's a decimal, if it's a fraction, if it's a radical, if it's anything not a whole number, technically it's not a polynomial function. And that's going to be important when it comes to finding or defining whether or not something is or is not a polynomial function. Now, polynomials are described by its degree, right? What is the degree? Well, let's go ahead and define it. So in mathematics, if we're not talking about angles and we're talking about polynomials, the word degree means the largest exponent in a polynomial. So a polynomial is defined by its degree. So let's go ahead and make a sort of like a 2-column chart here. One column would be a degree, and the other column will be the name or the type. If your degree is 0, that is to say you don't have any variables at all, you don't have any x's, we call this a constant function. If your degree is 1, we call it a linear function. If the degree is 2, we study this. This is all Unit 4. We call those quadratic functions. Let me capitalize it. If the degree is 3, we call it a cubic function. If the degree is 4, we call it a quartic function. And then there's technically names for all of them. Degree of 5 is a quintic. Degree of 6 is a hexic, so on and so forth. But honestly, once it gets beyond 4, we just call it generic polynomial. But at least for a good, 4 or 5 different classifications, up to 4. So 5 and beyond, there are names for them. We just call it generic polynomial. But I think, I expect you guys to know at least up to 4. Constant, linear, quadratic, cubic, quartic, and polynomial. And the last vocab word is end behavior. And this describes the behavior, aka the direction, a polynomial goes as x tends towards positive or negative infinity. That definition probably won't make much sense unless we do a couple of examples, which we'll get later on. So those should be the special vocab words for this section. We should know what a polynomial is. We should know what a polynomial function is. A polynomial function is defined by its degree, which is the largest exponent, and then depending on the degree, these are the names. So what are some? So let's tackle the lesson goals. One thing I'm going to expect you to be able to do is identify whether or not a given function is a polynomial, and if it is, I want you to rewrite it in standard form, right? So, are the following functions polynomials? If so, write it in standard form. State its degree, its type, and leading coefficient. So this will be a part A, part B example. So for the first function, we have f of x equals 3x cubed plus 4x to the 2.5 minus 6x squared. And for the second function, we have f of x equals x squared plus 3.7x plus 9x to the 4th power. So to answer this question, we have to again know what the definition of polynomial function is. So here's the definition of polynomial function. And what are the restrictions? There really is basically only one restriction for a polynomial function. This guy here, the n has to be a whole number. The coefficients can be any real number you want, whole numbers, fractions, decimals, positive, negatives, but the exponents have to be positive whole numbers. So that's all we're checking. So I hope we can see that letter A. Uh-oh, this is bad here. He is not a polynomial. That's it. That's all you have to write. Because the exponent is not a whole number. If we take a look at letter B, this exponent here is a 2. This exponent here, we don't see him, so it's a 1. This exponent here is a 4. All positive whole numbers. This is good. This is a polynomial. Yes, a polynomial. Since he is a polynomial, let's go ahead and do whatever the instructions ask us. the first thing it asks us to do is write it in standard form. We have to remember that standard form is a particular ordering. You go from biggest exponent to the smallest exponent. So scan the exponents again. 2, 1, 4. I hope everyone can see that 4 is the biggest, then 2 is the second biggest, then 1 is the third biggest. So you just go ahead and rewrite the terms in that particular order. So in standard form, you write the 9x squared to the fourth first, then the positive x squared second, and then the positive 3.7x third. The degree is the highest exponent, and here we can see that the highest exponent is 4. Knowing that the degree is 4, I know the type. The type is a quartic function. How do I know? Well, I just referred to this chart here. And last but not least, the leading coefficient. The leading coefficient is simply the number in front of the variable that has the biggest exponent. So in this case, the leading coefficient is 9. So that was a pretty simple problem. It's just reading and identifying. Now, the second task that we need to do is to be able to evaluate polynomials. And you guys have been doing this for forever, right? Evaluate f of, let's say, f of 2 when f of x equals 2x to the 4 plus 3x cubed minus 6x squares plus 3. This is simply plug and chug, right? That's what the word evaluate means. If I give you a function f of x and then I put it in a number inside of the parentheses, that just means in the equation, wherever you see an x, you change it into a 2. So let's go ahead and do that. F of 2 equals, whenever I substitute, I like to use parentheses. So instead of 2x to the 4, it's 2 parentheses 2 to the 4th, plus 3 parentheses 2 cubed, minus 6 parentheses 2 squared, plus 3. And then this might take some mental math, might take some calculator work. 2 to the 4th is 16. 2 cubed is 8. 2 squared is 4. Then go ahead and multiply. So that's the 32. 24 minus 24 plus 3. Hey, that's lucky. These guys cancel out. And I'm left with a 35. Okay, there we go. We evaluated. That's one particular goal. Now, this is called direct substitution. We didn't do any fancy gimmicks. We just went ahead and boom, plugged it in. But there is this thing called synthetic substitution. And it's just sort of a little neat trick. To quickly figure out what the answer is when you just want to plug and chug. So let's go ahead and do the same examples because we know what the answer should be. The answer should be 35. Right? So suppose I asked you, use synthetic substitution to evaluate f of x equals, what was the function again? It was 2x to the 4 plus 3x cubed minus 6x squares plus 3. When x equals 2, right? That's what we plugged in. So how you do synthetic substitution? Well, what you want to do first is make this L bracket. It's going to look weird. And then you're going to put the coefficients, that is the numbers in front of the x's, and the constants on this first row here. But what you want to do is make sure that every single exponent is accounted for. What do I mean? Well, if I start writing out the coefficients, 2, 3, so on and so forth, right? 2, 3, negative 6. Where did I get these numbers from? I got the 2 from the x to the 4. I got the 3 from x cubes. I got the negative 6 from x squares. If I were to keep up with the pattern, x to the 4th, x cubed, x squares, next should be an x, and then finally the constant. But do you notice, do we have any regular x terms here? Here's x to the 4, x cubes, x squares. I don't have a regular x term. So the idea is that if there's any exponents that are quotes missing, you have to put a 0 and then finally the constant. Whichever number you're evaluating at goes on the outside. Now this is why I like synthetic substitution. It only has 2 steps. You're going to add down the column, and then you're going to multiply by the outside number. Where you put your answers are going to be the important thing. I guess I should color code this. So I'm going to, I don't know, since I've used blue, I'll do this one yellow. And can you guys tell that's red? Or should I use purple? They all look the same to me. I'll use red. Okay. So the first step is to add down. Well, so let's go ahead and do that. No, notice this spot will always be empty. So if I added down the columns, that's 2 plus nothing. I'm going to put a 2 down here. And then the next step is to multiply by the outside numbers. You're going to always look at this bottom row here. So I'm going to take this bottom row 2 and multiply with the outside number. 2 times 2 is 4. I'm going to put it in the middle row. And then you basically rinse and repeat. Add down the column. 3 plus 4 is 7. Multiply by the outside number. 7 times 2 is 14. Add down the column. Negative 6 plus 14 is an 8. Multiply by the outside number. 8 times 2 is a 16. Add down the column. 0 plus 16 is 16. Multiply by the outside number. 16 times 2 is 32. Add down the column. 32 plus 2 is 35. And I always like to box my final answer. Hey, guess what? There's our 35 here, just as we got from the previous example. So all of this work says f of 2 is 35. Now, obviously, I did a whole bunch of extra writing. I wouldn't typically do this, all this writing. You know, I wouldn't typically write this part here. I wouldn't typically write all the little plus signs or the arrows. I would only just basically write the numbers. I did all this extra writing for the purpose of the notes, but I promise you, if you understand this method, it's going to make math a lot easier in the future. So I know it looks messy. I know it looks scary. You know, hey, can I just plug it in? It's a lot simpler. Yes, you could, but learn the method of synthetic substitution. It's going to save you a lot of headache. The next thing we need to be able to do is talk about the end behavior of polynomial functions. And this is sort of the idea. Polynomial functions, they're very confined, right? If you think of just a generic equation and you wanted to graph them, it could look anything you want. Polynomials, they basically look one of 4 types here. And so let's just sort of make this chart here. Polynomial function, in terms of the ends, can go up on both sides. I don't know what happens in the middle. Is it a regular parabola? Is it a weird squiggle? I don't know. So I'll do a dotted line. But a polynomial function can go up at the ends. They can both go down at the ends. They can go up and to the left and down to the... Actually, let's go this direction first. Down to the left and up and to the right. I don't know what happens in the middle. Or the exact opposite, up and to the left and down to the right. Again, I don't know what happens in the middle. How do I know which format or what end behavior I have? It's all dependent on the degree and the leading coefficient. So that's why in the vocab, I wanted us to really identify what the degree of a polynomial function is and what is his leading coefficient. In the first case here, these only happen when the degree is even and the leading coefficient is positive. In the second case, it only happens when the degree is even and the leading coefficient is negative. In the third case, it only happens when the degree is odd and the leading coefficient is positive. And in the last case, this only happens when the degree is odd and the leading coefficient is negative. Now we can informally describe the end behavior. let's take a look at the left picture. Oh, it would be true to say this graph goes up and to the left and up and to the right. The third picture, it's true to say the graph goes down to the left and up and to the right. But when we write end behavior, we sort of want to do it mathy. We don't want to just use those informal terms. Well, let's take a look at a regular coordinate system here. Let's see here. Let me go ahead and write down the end behavior first. It's going to look really weird. It's going to look like it's a different language, but then I'll explain what it means. So for right now, just copy and follow along, and then we'll talk about why it is the way it is. So in the first case, if you have this type of situation, if the end behavior is up in both sides, if the degree is even and leading coefficient is positive, how do I write the end behavior? I would say the function f of x approaches positive infinity as x approaches negative infinity. The function f of x approaches positive infinity as x approaches positive infinity. What the heck? Trust me, follow along, just copy it down and I'll explain it later. The second case, f of x approaches negative infinity as x approaches negative infinity. F of x approaches negative infinity as x approaches infinity. The third case, f of x approaches negative infinity as x approaches negative infinity. F of x approaches positive infinity as x approaches positive infinity. And in the last case, f of x approaches positive infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. Lots of infinities, lots of arrows. What does this mean? Believe it or not, it is the same informal statements that we've made. We just did it in math speak. Like, for example, the first guy here. We all agree, oh, it goes up and to the left and up and to the right. That's exactly what this says, just using math symbols. And how do I read that? How do I know what each symbols mean? Well, if you look at a coordinate system, right, I hope everyone can agree that, I mean, if you don't know your up, down, left, right, this is to the right, this is to your left, this is up, and this is down. Now, this is also a coordinate plane. This is x-axis and this is your y-axis. Don't we agree that x's are positive to the right and then x's are negative to the left? What about the y's or f of x? Remember, y is the same thing as f of x. Aren't the y values or the f of x values positive going up? And aren't the f of x values negative going down? Well, that's what all these infinities say. For example, if you have this end behavior, notice how it's going up and to the left? Well, up and to the left. What's up and to the left? Hey, f of x is positive when x is going negative. F of x is positive when x is going negative. That's exactly what that infinity notation means. What about this side here? Oh, up and to the right. Up and to the right. F of x is positive when x is positive. F of x is positive as x approaches positive. So this arrow notation of describing end behavior, it looks scary and intimidating, but it's just describing what you see. Up and to the left, down to the left, up and to the right, down and to the right. You just have to know what direction the f of x and x is approaching. But if you know how a regular coordinate system works, you got this. Right. So let's just do a quick example here. Describe the end behavior of, let's say I wanted to do, I don't know, f of x equals negative 2x to the 7 minus 5x squared plus 6x minus 1. Well, the first thing you want to do is look for the degree. So where is the degree? What's the biggest exponent? This 7 here. Now you want to classify the degree in the leading coefficient. Hopefully we can see that the degree, which is 7, is odd. The leading coefficient, which is -2, is negative. Right? So we have an odd negative situation according to our chart. Odd negative would be this guy here, up and to the left, down to the right. So sure, you can just memorize this or have it in your chart and copy it down, but let's see if we can't just do it logically. So if you know it's up and to the left and down to the right, so I know the end behavior is up and to the left and down to the right, let's go ahead and say that. Up are the y values, f of x. If I go up, are the y values positive or negative? Of course it's positive. If I'm going to the left, are the x values positive or negative? It's going to be negative. Down and to the right. Well, if I'm going down, are the y values positive or negative? It's negative. If I'm going to the right, are the x values positive or negative? Going to the right here. Going to the right. X values are positive. Easy peasy. Right. So you got two choices. You can practice reading end behavior, right? So you can basically memorize the first half of the chart and then figure out the arrow notation, or you can memorize, undo. Or you can memorize the whole chart. It's completely up to you. Now, end behavior just gives you a hint as to what happens on the ends. How do I figure out what happens in the middle? I hate to say it, there is no big secret. You just got to use a table of values, right? So that's it. I mean, sorry to be anticlimactic, but to finish our last goal, just use a XY table. So suppose I ask you to graph f of x equals negative x cubes plus 2x squares plus 2x minus 1. Now, unlike quadratics where we have special tips and hints, back in Unit 4 I said, hey, if you want to graph a quadratic, start with the vertex. With regular polynomials, we don't have that luxury. So we're just going to have to pick our own x and y values. Since I don't have anything to go by, I always like to stick with my standard -3, -2, -1, 0, 1, 2, and 3. Sometimes it works, sometimes it doesn't, but that's what I always like to start with. So you just go ahead and plug and chug. Right. So I'm not going to spend all time showing the math. It's just a mental math thing. It's just a calculator thing. But if you're to plug in a -3, you're going to get a 38. Plug in a -2, you're going to get an 11. Plug in a -1, you get a 0, -1, 2, 3, and -4. Obviously, if you get something that's ridiculously big, you don't have to plot it. So obviously, I can't plot -3, 38. I just can't fit 38 tick marks. But just plot as many as you can. The more points you have, the nicer the picture is going to turn out. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11. I can fit 11. Yay. 2, 3, 4, 5, 6, 7, 8, 9, 10. So obviously I'm going to skip -3, 38. So -2, 11. -1, 0. 1, 2. 1, 2, 3. Oops. Oh, I totally messed this up. Let's try again. Sorry, guys. -2, 11, -1, 0, 0, -1, 1, 2, 2, 3, and 3, -4. So, I mean, I don't expect a picture perfect graph, but, just do the best you can when you connect the dots. So if I connect the dots, it looks like it does something like a roller coaster, right? There you go. That's a pretty decent sketch. And the end behavior should match, right? Because here's the leading term. See how it's the leading coefficient is negative and the degree is odd? Well, what does negative leading coefficient and degree of odd tell us? Odd degree, negative leading coefficient, up and to the left, down and to the right. And what does our graph do? Up and to the left, down to the right. It's pretty cool. So that's it. That's the big secret. How do you graph? Just make an XY table. I like to use these as the starting values, but use as many X values as you need to generate a pretty decent picture. So that is it. That's 5.2. Have at it.